normal tissue. This makes sense because p53 is a tumor suppressor, so it's usually inactivated or dysfunctional in the breast tissue, cancer tissue. Similarly, I can also analyze cyclin E1, EGFR, and also p53 expression at the same time in the breast cancer. Okay, so I just need to type those three gene names over here and select cancer with normal analysis and select breast cancer type. And this is heat map I'm going to get. This is 4 different probes showing cyclin E expression and EGFR and this p53. Okay, and here is 0 meaning normal tissue, and this is a couple of the cancer subtype. This is different data set because this breast cancer. Actually, right now, because this breast is contain about 2,136 samples. This is the largest data set in breast cancer and also in lymphoma as well. Some of the questions I can ask is, okay, so what are the genes that co-express with p53 in breast cancer, or the gene that co-express with HER2 or CCNA, secondly E1 in melanoma, for example. Okay. So for the first question about what are the genes that are co-expressed with p53 in breast cancer compared to normal tissue. So what I'm doing is I'm going to type p53 in the search box here, and then select cancer versus normal analysis, which is right here. Okay, and then select cancer type, breast cancer, and this is the heat map I'm going to get. So you see p53 here. Of course, p53 correlation to p53 should be 1 because it correlated itself. And after that, I have a couple of other genes down here, which have a quite high correlation score, meaning that those genes are tightly co-expressed with p53. So probably those genes could be the downstream targets of p53. Some of the questions you can ask is, for example, which genes are mostly overexpressed or downregulated? In other cases, in brain and central nervous system cancer compared to the corresponding normal brain or central nervous tissue. This is a very commonly asked question in cancer research. We'd like to know the difference between the cancer tissue and the normal tissue. So OncoMind can allow you to answer that question very easily. Okay? You just need to select the cancer type, filter, for example, like brain cancer, cancer with normal analysis, and you just let OncoMind select some of the data set concept for you. And for example, here you're going to see a list of genes that are commonly overexpressed in the brain cancer. This is group number 1 here. This is the normal brain. Group number 2 here is I cannot read it, but I think it's a type of brain cancer. Yeah. So this heat map, when you see a blue color, meaning that it's downregulation, a red color, meaning upregulation. So you see a very big contrast between the normal brain and the brain cancer. So it is the gene that's mostly upregulated in brain cancer. Sometimes OncoMind also established some concept for us to use. Concept meaning that it's a predefined filter for you ready to use. You don't have to type anything. Just use what they already established. For example, using the concept analysis, we can select and understand what are the top 1% overexpressed genes or top 10% underexpressed genes in each cancer type compared to normal tissue. So in order to use a concept analysis tool, we just need to select the concept tab. So from the beginning of our lecture until now, we mostly use a dataset tab. And now we're going to switch to concept tab. So you see here, this is some of the predefined, pre-established analysis standard that OncoMind already created. If you would like to know more about how to use OncoMind, then you can use this link. It's a good PDF file for you to use. Okay, and I think it's also HTML file as well. So here you have introduction to OncoMind, getting around OncoMind, creating bookmark, etc. So if you click on each question, it's going to give you very good guidance. This is my contact information again. And if you have any questions, please feel free to send me an email. So now what I will do is show you how to use the Oncomine with a live demonstration. Okay, so this is the web page of Oncomine. You use user ID and password. So you can log in. Okay, so this is the search box. You can type your gene of interest, for example, like p53 here. I'm going to give you a couple of suggestions, like p53 tumor antigen, signaling pathway, transcription factor, or the gene. So I select the gene here. This is loading data. So you can see now in Oncomine there are 680 datasets that contain p53 mRNA status. You can also select cancer type. If you want to do a primary filter, then you select here. For example, cancer type, you can select breast cancer, for example. Now we have 125 datasets. See breast cancer. Very slow. Please be patient. So I can type breast cancer here. Okay, type breast cancer. Is a cancer type. Okay, select cancer type here. You see now it's search cancer type breast cancer. I can do a cancer versus normal analysis. And you can also filter the variable by p-value, where you can select one change in the gene rank. So here we have about 14 different data sets satisfy my requirement here, containing p53 in the data set, containing cancer normal versus normal analysis, and it must be breast cancer. So I have here a couple of interesting data sets. For example, I select something breast 2. This number of breast show you like how many patients are there in that data set. For example, I just select solely breast 2. Okay, and this is what I get. So right here, group 0 means the no value. This is a normal breast tissue. And I also have number 1 here, only I think 2 patients. It is a fibroadenoma. For number 2 here, this is a ductal breast carcinoma. And please pay attention that this is on the y-axis. This is a log to median center ratio. So that's the reason why you can have a negative and positive result. And here, this is the reporter. This is the probe ID. If you select, in this case, they only have use one probe. This detect 53 status. Some other data set can use multiple different probe. So let me select, for example, like ECGA, right, containing about 593 patients. Okay. And here you can see they have 3 different probes to detect P53. So it really depends on which probe you use, then you may have a slightly different result. But the recommendation to choose the right probe is that probe needs to have very strong and specific binding to your mRNA of the gene of interest. Okay. For example, I'm getting tired of receiving all of these bar graphs. Okay, it's too much to compare. So I just select cross plot. And it will give you a summary of this data. And one more notice is when you select, you use different data set, you will may end up with different results. So this is quite normal because if you notice each data set here only contains about 100 to 200 patients, something less than that. And those numbers, small number amount of patients, will not be enough to represent the whole population of breast cancer patients. So I recommend that if you do analysis, you should combine multiple data sets in your analysis to increase the number of patients. Okay, so now we select ECGA first, select the box plot. This is what I get. This is the no value. This is right here. Okay. When you select here, you have maximum, the 90th percentile, median, P53, etc. And then some of the cancer type, for example, this one, this is number 4, which is intraductal pre-preformed breast adenocarcinoma. 3 patients, they have a little bit low P53, etc. Okay. We can also, if you want to delete all of this filter, just select it, delete it, then it will remove all of those filters for you. So when I finish, let's remove all the filter. You see, this is the number of total data set. You see, I prepared this lecture about 2 weeks ago, and at that time they have about 674, 84 something data set. Now they have 715 data set and more than 86,000 cancer patient samples. So you see, they keep updating their database very frequently. So for that, another demonstration is we can do a co-expression analysis of, for example, like P53. So just type P53 in the search box. Okay. P53. Select breast cancer. primary filter. They have multiple types of analysis type, like core expression analysis, differential analysis, or outlier analysis. For dataset type, we have something like, and recently in July, or cell line panel dataset, automated reference dataset, the TCGA, etc. Data source, let's say, is a public, early public. Cancer type is a breast cancer, of course. We can select a sample filter, like we have cancer sample site, whether it is as a primary tumor or metastasis. And sometimes some of the advanced cancer researchers would like to have this kind of analysis. Or a physician may like to have a clinical outcome. For example, like metastasis of the event status, patient treatment response, recurrent status, or survival. A molecular subtype, like it's a biomarker or methylation type, microsatellite mutation, or pathology subtype like grade, like 1, 2, or 3, or stage type like 0, 1, 2, 3, 4, or cell line name, pathway changes. For example, like inspection into the lungs, into the in vitro culture, or drug sensitivity, like chemotherapy sensitivity or targeted therapy sensitivity. Treatment, chemotherapy, control treatment, hormone treatment, natural ligand treatment, or targeted therapy. Or sample type, for example, like cell line, clinical specimen, or primary cell culture, or xenograft. Xenograft is a mouse model. Xenograft. In a tissue subtype, epithelia or stroma. Demographics, the age, race, sex, smoking status. You will select the dataset filter. You can have a data type, a DNA or RNA, or dataset name. This is a lot. Or dataset size, like how big the dataset your computer can handle, and just or Google can handle, or something you like. For example, some people like to do a large dataset, more than 151 sample, or some people just do an average size dataset, or some people like to analyze smaller. A platform, like mentioned earlier, right now they have 3 major companies with Affymetrix, Agilent, and Illumina. So Affymetrix is the most popular, and after that is Illumina or Agilent. And also a lot of homemade, custom-made platform as well. Concept. The concept, you can have biological concept or mutation concept, etc. So I wouldn't go too much in detail. I will leave you. I think you can analyze all of that at home. So for example, in this case, I just do co-expression analysis, for example. So I select co-expression analysis. So you see, here I have about many data sets that satisfy my requirement. So I can filter again by setting a quite stringent filter. Like I want only to look at the data set that have a huge difference in p53 expression with the comparison between the normal and the interstitial. So I just select, for example, any data set have at least 4 times 4 changes. So I'll check it out. setting that one change filter. Then you see this color right here. This color is from very red to light red and sometimes no color. It's meaning that this red color right here represents that this in this data set there's a huge difference between the p53 expression in the normal tissue compared to that in the cancer tissue. So for that, I just select mild breast 3, for example. This is data set submitted by Dr. Ma, and this is for breast cancer. And this is the third data set that his group submitted. This contains about 60 patients, and the average co-expression of the genes in this analysis is about 0.805. So it's up to select here, and just wait a little bit. Okay, so here I have double breast carcinoma. Oh, I'm sorry, I forgot to select the cancer with this normal analysis. So I need to add that. So I just want to compare normal tissue and the cancer tissue. So I'm going to type cancer. Very slow. Okay. So cancer versus normal analysis. Let's see. So the question is about the name of the data set. For example, here you have solely breast, for example, Ma breast 4. Okay. So when you see Ma means this is the last name of the first author of that paper. Usually, what they do is that when people publish a paper, they will ask that group to make the data public. Okay, so they contact usually either the first author or the last author, the corresponding author of that paper. In this case, Ma is the last name of the first author of that paper. Okay. And breast meaning that this is breast cancer data set. 4 meaning that this group has submitted multiple data set, and this is the data set number 4. And it contains 66 patients. So for example, I select here breast 4, and let's see what happened. Right, let me expose it. Yeah. So it's very slow. But anyway, you can see here, for example, in the solely breast data set, p53 expression is right here. Okay. And we have another very strange name. It's loose P1 or something. I never seen it in my life, but this gene is highly correlated with p53. I would say not highly, but quite significantly. Because for the correlation analysis, anything close to 0.8, 0.9, we consider a strong correlation. Everything about 0.5, 0.7 is quite significant. Everything below 0.5 is okay, quite weak correlation. Okay. So in this case, this person also have multiple type of use multiple probe to analyze BP3 expression at the mRNA level. And one thing you should be aware is these probes have different level of specificity and binding strength. Okay. For example, here you have this probe -A.18, this probe -3P-18, and same thing with -X-18. So the best probe is this one. So anything you have X right here, don't use it. This is not specific. Okay. Something here, -A.80, a little bit more specific, but they can detect some of the other variant and strip of p53 or p53 family member, like p63 or p73. So the most reliable probe is the one just dash